Hey guys, Dr. Thomas. This is the last part of the chapter 14, part 2 videos. We're going to start on slide 26 from the PowerPoint. We just introduced mechanisms in the last video, talking about multi-step mechanisms, and we want to be able to look at a multi-step mechanism and be able to come up with the rate law for the overall reaction. Okay. Now we specifically said that when we have a multi-step mechanism, the overall rate law will be determined by the slow step. So there are two scenarios that we can encounter regarding that possibility. Number one, if the slow step is the first step, then basically we can just write the rate law of that step, and then that is the overall rate law, and we're pretty much done. All the steps that come after that are faster steps, so they happen very quickly. They don't really play a big part in the overall rate of the reaction. Okay, a little bit harder though, if we have a case where the first step is a fast step, that means the slow step is going to come up as a later step in the process. Then we have a little bit more math we have to do, specifically because when you write the rate law, when the slow step is a later step, it will typically involve an intermediate, and when we have an intermediate in a rate law, that is not a proper form for writing your rate law, so we have to do some substitution to get rid of that. All right? So, first example, if I look at an overall reaction, I have NO2 plus carbon monoxide yields NO plus CO2. Let's say we go to the lab, we do some experiments, we determine, maybe by the method of initial rates, we determined that the rate law for this reaction is the rate equals K times NO2 squared. So the NO2 molecule is second order, and then since the other reactant CO doesn't even appear in the rate law, that means it must be zero order. Okay? Now, I can already tell at that point, since my orders of my two reactants don't match the coefficients from the overall reaction, that means that this reaction has to be happening as a series of steps where if the first step is the slow step, which is going to be the assumption for this problem, if the first step is a slow step, it's only going to involve two NO2 molecules. It's not going to involve any COs. The CO is going to come in a later step. It'll be a fast step, which means if it's a fast step, it doesn't have a major role in the overall rate. So that's why CO doesn't show up in the rate law. So the first step is the rate determining step, which is called the slow step. The coefficients from that step become the order. So essentially, if I were going to start trying to come up with a mechanism, and again, as a chemist, we study the reaction, we determine the orders, but then we want to kind of understand how the reaction happens. So if we want to derive the step-by-step process by which a reaction happens, we want to develop a mechanism. Okay? Well, from the experimental data, I know that this mechanism is going to start by saying, okay, two NO2 molecules are going to crash into each other. And then when they crash into each other, some bond's going to break, another bond might form, but then from that point I can start thinking about what the possibilities are. And with a little bit of chemistry knowledge, which is this knowledge is something you don't have to come up with any mechanisms yourself, but I kind of want to talk through that process because when you get to organic chemistry, you will have to be able to do this after we've covered it in class and you've been taught how to approach it. So, possible way this reaction could happen. Okay, it's very common that when two molecules collide with each other, sometimes there's something that happens called an atom transfer. Basically, these two NO2 molecules crash into each other. One of the oxygen atoms is going to break off one of the molecules and then reattach to the other one. Okay, so my two NO2s, the one that loses an oxygen becomes NO. The one that gains the oxygen becomes NO3. Okay, so that's a possible way that this reaction could get started. Now, if that happens, what I notice is NO is actually one of my products that I needed in my reaction. So my first step, I made one of my products that I need. The other molecule that I made, though, NO3, doesn't appear anywhere in my reaction. So that means if I made it in one step and it doesn't show up in the reaction, that means I need to get rid of it later. Okay, so that's what an intermediate is. It's something that is formed in an early step of a process, but then later gets used up as a reactant. So it's only present in the middle of the reaction, not at the beginning or at the end. So my second step that I write, I may want to do two things. One, I need to get rid of my intermediate, and I need to form the other product that I don't have yet. So to do that, I'm going to have my NO3 that I just made from the first step, and then I'm also going to bring in my other reactant, CO, which we said CO is not part of the rate law, so I knew it wasn't part of the first step, so now I'm going to bring it into the second step. If my intermediate and my other reactant collide with each other, again, an atom transfer can happen where the NO3 gives an oxygen to the CO, forming CO2, there's my other product, and then actually the NO3 gets turned back into NO2, which was one of my original reactants. So if it floats away, then it could actually bump into another NO2 molecule and start the whole process over again. Okay? So essentially, in this mechanism, I can explain how both my reactants got used, how both my products got formed. I made it intermediate and then used it. So right now, everything looks pretty good for these two steps that I've developed for this mechanism. Now, I don't know if it's right or not, but at least everything I did is a possible way that this process could occur. So, just putting it all together, these are the two steps that I derived. Now, specifically, the first step is often the slow step in a mechanism because if you think about it, the reactant molecules are usually fairly stable. And these molecules, when stable molecules kind of crash into each other and bounce off the walls and all that kind of stuff, most of the time those molecules are just going to hit each other and bounce. No reaction occurs. But every once in a while, if they hit each other hard enough, then you're going to have a bond break or a bond form, right? So if they're stable molecules that usually bounce off each other, then the progression of that first step is usually going to be pretty slow. Okay? Now, once we form an intermediate, the intermediate, while I won't say it's completely unstable, it's usually less stable than the reactants. Okay? And once I form an intermediate that's not very stable, unstable compounds tend to react quickly. As soon as they bump into something else, they want to react to regain the stability that they don't have anymore. Okay? So that's why the first step tends to be slow because you're dealing with pretty stable compounds. And then when you get into the second, third, fourth steps, those steps tend to go faster because you have less stable species that exist at that point. Sometimes they're ions, sometimes they're radicals, which a radical is a atom or molecule that has an unpaired electron. But anything about it that makes it unstable is going to make it want to react faster. So if we look at a mechanism, okay, so let's just say this mechanism is provided, you should be able to write the rate law for any step that's there. The rate law of the first step would be rate equals K, and if it's the first step, we'll sometimes call that K1. Okay, so rate equals K1 times, there's two NO2 molecules here, so it's going to be NO2 squared. Okay, we already saw that on the previous slide. That's the rate law of the first step. That's the slow step, so of course that's the one that matters the most. But we should also be able to write the rate law of the second step. The rate law of the second step would be rate equals probably K2, subscript 2, excuse me on that one, and then times NO3 to the first power, because there's a 1 in front of it, times CO to the first power. Okay, now, I can write a rate law for each step, but the one that controls the overall rate is the slow step. Okay, and then finally, that's it for that one. Okay, so things we look for. If the first step is the slow step, the rate law of that step equals overall reaction rate directly. We should be able to add the steps up, cancel things out, and get the overall reaction. That's another key thing that we mentioned. Every step has to be balanced. If all these things work, then this is what we call a plausible mechanism. Again, I don't know if it's right. The only way I can actually get some kind of chemical support for that would be if during the reaction somehow I could measure or study the actual intermediates that are formed, if I can isolate them and then somehow analyze them to prove that NO3 was produced during the middle of that last reaction, that would be supportive evidence to make it seem like my mechanism might be right. But a key is we can never prove that the mechanism is right. All the measurements that we're doing are indirect measurements. We can't actually see the molecules themselves, so we can't tell exactly which bonds are breaking, which bonds are forming. We can't see it. No microscope is strong enough to see individual molecules and what they look like. Okay? So everything we do, we're getting supportive evidence so that we become more and more sure about the mechanism, but we're never going to be 100% sure it's right. Okay? On the other hand, though, there are things we can do to prove a mechanism wrong. It's easy to prove a mechanism wrong. Okay? That happens every day around the world. Their reactions are being studied. They come up with a mechanism that they think might be right. They do some studies about it. They realize it's wrong, and then you throw it out. Then you have to come up with a new mechanism. When you get a good mechanism that you can get a lot of evidential support for it, then you can actually continue on and think, okay, this is what we're going to use, and then try to keep developing more and more support for it. That's how mechanisms that you've heard of, like the Krebs cycle, glycolysis, the citric acid cycle, a lot of those biological cycles that are done, they have lots and lots of support for those mechanisms because they've isolated intermediates. They've kind of got enough evidence about each of the steps that they're pretty sure the overall process is correct. All right, so another reaction. We have two nitrogen monoxide molecules reacting with fluorine to form two O and F molecules. If this was an elementary reaction, if the reaction happened in one step, then I should be able to take the coefficients from the beginning and write the rate law. Okay? So if that were true, if there's a one-step reaction, the rate law would be rate equals K times NO squared times F2. This would be a termolecular reaction. Remember, a reaction that has three molecules colliding all at the same time, which an elementary step has to be a singular event. So if this was a single-step reaction, that's what the rate law would be. All right? Now, if I go to the lab and study this reaction, do the method of initial rates, we can actually experimentally determine that the true rate law for this reaction is the rate equals K times NO times F2. That is not the same as the one that we had above, so automatically I know this is not a one-step reaction. This must be happening as a series of steps. At that point, I can start trying to figure out how it occurs. Now, from my experimental rate law, I know that the rate limiting step is going to involve one NO molecule and one F2 molecule based on the orders. So I can start my mechanism, NO plus F2. Again, we might try an atom transfer where one of the fluorines gets transferred over to the NO to make O and F and F. Again, I can look at that and say, okay, the O and F, that's one of my products that I needed to form. Okay, I need to make two of them, but I formed one of them in the first step, and then I form a fluorine atom by itself. That would be a fluorine radical. That's very unstable. It's very reactive. So as soon as it bumps into another molecule, it's going to try to react. Well, if that fluorine in the second step bumps into another NO molecule, it's just going to bind onto it and make the other O and F molecule that I needed. So again, the second step gets rid of my intermediate, and it forms the other product molecule I need. This seems like a pretty reasonable mechanism. I can write out both my rate laws. Okay? Again, I could predict, you won't have to do this, but I could predict that the first step is probably going to be the slow step based on the fact that it's two stable molecules forming an unstable intermediate, so the energy is probably going to go up, it's going to have a high barrier. So first step is a slow step. If you look at that, it does match up, which is how we started the mechanism in the first place, but the rate law of that first step matches up with my overall rate law. Once again, though, just the warning, just because everything looks good about this, it doesn't mean this is necessarily the correct mechanism. We would have to do further studies to support it, and hope that it doesn't get proven wrong by what we find out. All right, so now we come to the other possibility. What if the first step is a fast step and the slow step comes later? Okay? In that case, there's going to be more math we have to do, so let's explore it. So I have a reaction, 2 NOs plus 2 H2s yields N2 plus 2 H2Os. The experimentally determined rate law says the rate equals K times NO squared times H2. Okay, now again, my orders here do not match up with my coefficients, so clearly this is a multi-step mechanism. Now when I start working with this, it is known from other studies and reactions that when I have nitrogen monoxide in a container, those molecules can collide with each other. Sometimes they're going to bind with each other and form N2O2. Okay? But at the same time, the N2O2 molecules that we form, when they start flying around and bump into the wall or each other or any other things, sometimes they break apart again. So the first step, notice the double arrow here, the first step is called a reversible step. Okay? So this reaction is a fast reaction. When they bump into each other, they just bind, and then when they bump into something else, they fall apart. So the reaction is fast in both directions. I could write a rate law for the forward reaction. That would be the rate of the forward reaction is going to equal K1 times NO squared. Okay? Then I can also write a rate law for the reverse reaction. For the reverse reaction, that means I'm starting on the right and I'm going to the left. The reactant is N2O2. So the rate law is going to be the rate equals, the rate constant is still the first reaction, so we call it K1, but since we're going backwards, we're going to call it K minus 1. Okay? Now, K1 and K minus 1 are not mathematically dependent on each other. Like some people think that they're like inverses of each other or something like that. They're really not. Okay? They're just two different rate constants. K1 is for the forward reaction, K minus 1 is for the reverse reaction. Okay? But the reverse reaction rate law would be rate equals K minus 1 times N2O2 to the first power. All right, so I can write both those rate laws. The second step, N2O2, some of the ones I form here are going to bump into H2 and form N2O and H2O. I can also write a rate law for that step. And then once that happens, N2O reacts with H2 to form N2 and H2O. Again, if I add all those up, cancel things out, it does give me my overall reaction. So I could write rate laws for, I can write two rate laws for the first reaction, forward and reverse. I can write a rate law for the second reaction. I can write a rate law for the third reaction. Okay? The one that's the most important is the slow one. So if I write that, the overall rate law should be the rate equals K2 times N2O2 times H2. That's the rate law of the second step, which is the slow step. Now, we do have a little bit of an issue, though. This rate law that we just wrote, N2O2, does not show up in the overall reaction. It's an intermediate. We are not allowed to leave intermediates in the rate law. It's just not a proper form. So the reason for that is that intermediates tend to be unstable compounds. They only exist in low concentration, and their concentration kind of stays fairly constant because as you form it, you use it. So it's just not mathematically sound to include the intermediate. So we have to do some substitutions to get rid of the intermediate from our rate law. So expressing the rate law, including an intermediate in the equation, is not allowed. We're going to rewrite the rate law, and we're only going to use reactants. Now, I will say, if you go into upper level classes, analytical chemistry, even biochemistry, there are cases where your rate law actually can include reactants and products. Okay? Usually, like reactants, have positive orders because as you increase the concentration of reactants, the rate of the reaction usually increases. If a rate law includes a product, again, in biology, we learn there are reactions where as your body produces some compounds, that compound will go back and inhibit the reaction. So that can be a, competitive inhibitor or non-competitive inhibitor, that kind of thing. So as the product concentrations build up, the reaction is going to get slowed down. Okay, that would be a molecule that has a negative order in the rate law. Those can happen, but we're not going to see them in this class. Okay, in our class, the rate law is only allowed to have reactants, and if you have an intermediate, we have to do some work to get rid of it. All right, so in my mechanism, if you look back at the 3 steps, you would see that the N2O2 can react in 2 different ways. It can react in the first reaction. It can go back to reform NO. That's the reverse reaction of the first reaction. Or the N2O2 can go down to the second reaction and react with H2 to form N2O and H2O. Okay? Since it can react in 2 different ways, it's getting used up pretty quickly. We're going to focus first on step 1 of the mechanism. That's the reversible step. We're going to write both rate laws. If we write the rate law of the forward reaction, that was K1 times NO squared. And we write the rate law of the reverse reaction, that was K minus 1 times N2O2 to the first. To write both those rate laws, what we learned, and again, this is a chapter 15 thing, but if it's a fast reaction where the reactants can react to form products, but then as soon as I form the products, then the products can actually go back to reform the reactants. Those 2 things are going to quickly get to equilibrium where they balance each other. So the molecules are moving left and right, but the rate of both directions are equal. So therefore, I'm going to set their rate laws equal. Okay? Now once I do that, if we look at the next slide, here are my 2 rate laws. This is the forward reaction. This is the reverse reaction. Once I set them equal, I'm then going to mathematically isolate the intermediate into O2. So what I'm going to do is I'm going to divide the K minus 1 over. So I'm going to say into O2 is going to equal K1 over K minus 1 times NO squared. And then I'm going to substitute all that into the rate law for step 2, which we said that's the slow step. But I'm trying to get rid of the N2O2. So where it did say before for the second step, rate equals K2 times N2O2 times H2, I'm substituting all that stuff in for the N2O2. And then once I do that, I have 3 K values there, K2, K1, and K minus 1. I'm going to combine them all to give me my overall rate constant. So again, I'm going to go back to having 1 K value once I combine those. But I end up with my new rate law for the second step. It's the same thing, but with substitution going on. Rate equals K times NO squared times H2. All right? So that's the rate law for this reaction. Now, a side note. If I looked at this, and if I asked you, is this reaction unimolecular, bimolecular, or termolecular? If you look at the rate law, it looks like with NO squared times H2, it looks like it's a ternary reaction, termolecular reaction, because there's 3 molecules involved. But that's actually a trick. If you look back at the mechanism a couple of slides ago, step 1 involved 2 molecules, so it was bimolecular. Step 2 involved 2 molecules, it was also bimolecular. And step 3 involved 2 molecules as well, so it's bimolecular. So all 3 steps were actually bimolecular. And if you remember, we said most reactions are bimolecular. You do sometimes see unimolecular. We rarely see termolecular. So even though the rate law here makes it look like we have a termolecular slow step, it's actually not true. It's just the result of the substitution that we had earlier. All right, our last topic, almost done, catalyst. So a catalyst is a molecule or chemical that's added to a reaction to speed it up. Okay. Now the way it speeds it up, A catalyst will increase the rate of reaction by lowering the activation energy. How does it lower the activation energy? It doesn't take the transition state up here and just bring its energy down. What happens is we're going to do the reaction in an entirely different way. Instead of going straight up a mountain, we're going to find a way to go around the mountain. Or we're going to break that one huge hike into smaller steps where we climb a little bit at a time. And if we can break a large activation energy, which corresponds to a slow reaction, if we can break it into a lot of steps that have small activation energies, we can get through a lot of small steps faster than we could get through that one huge activation energy that's blocking the reaction from occurring. Okay? Now, a couple of things. Number one, it changes the entire mechanism by which the reaction happens. So if we look at how a reaction happens with a catalyst or without a catalyst, it's just not even comparable. Okay? Now, we do have the same reactants and we do have the same products, but the way we get from one to the other changes. All right? Another key, if we're looking at a mechanism, a catalyst, when we add a catalyst, sometimes the catalyst will be used up temporarily or change its chemical form temporarily, but by the end of the mechanism, a catalyst has to be regenerated. If we start with a catalyst in the container, when we finish, we should still have the catalyst present in the container. Okay? Now, in a mechanism, the way we recognize that, a catalyst will first appear early in the mechanism as a reactant, and then later in the mechanism, it'll be a product. So it's there in the beginning, it gets used, and then before we get to the end, it has to be reformed. Okay, so it's a reactant, then a product. That's the opposite of an intermediate. An intermediate will be a product first, and then a reactant. All right, so quick example. So hydrogen peroxide. If I take hydrogen peroxide, H2O2, if I just leave it in my medicine cabinet at home for 2 years, over a really long time, it will decompose into water and oxygen gas. So just slowly, as it breaks down, oxygen gas is going to bubble out. And eventually, in the bottom of my shelf, I'm just going to have water. The hydrogen peroxide will slowly disappear. But like I said, that takes a couple of years. The reason it takes so long is that it has a pretty high activation energy that makes it a slow reaction. All right, now, if I add a catalyst, I can speed it up. So an example of this, if I add, it shows it separately, but if I add hydrobromic acid, HBr, again in solution, they're going to split, so that's why it says H plus and Br minus. But if I add HBr, that's going to start a reaction to change how the hydrogen peroxide decomposes. And instead of it happening in one big step, when I add HBr, if this graph is accurate, I don't actually know that it is, but I assume it is. If it's accurate, my hydrogen peroxide is going to break down in 2 smaller steps, where the activation energy, the first step is here, the activation energy, the second step is here. Both of those activation energies are a lot smaller than the original one, so the reaction's going to be able to get through those 2 steps pretty quickly. And I think if you do this reaction, it'll be fast enough that if you sit there and watch it for a few minutes, you're going to see the oxygen bubbles coming out of the solution. So it'll be fast enough that you can actually observe it happening. Whereas normally, hydrogen peroxide on your shelf at home, you can sit there and stare at it for hours and hours and hours, and it's so slow that you're not going to notice any change. Remember, it takes years for that to happen. Okay? Now, another way we can catalyze this reaction is actually, if I have an open cut on my arm and I pour some hydrogen peroxide on it, there are chemicals in my blood, specifically they're iron-containing compounds like hemoglobin or something like that. I don't know the exact form of it. But the iron in my blood will catalyze the decomposition very quickly. And everybody knows when you put hydrogen peroxide on an open wound, it starts to bubble like crazy. That's this reaction happening very fast. Okay, now in your body, naturally occurring catalysts in your body are enzymes. So, next slide. Enzymes are catalysts in your biological system. So again, the picture relates to the same compound, but enzymes tend to be very specific. Again, when you go to biology, there's a lot of terminology they use, like the enzyme. When the reactant comes to the enzyme, the reactant's called a substrate. Usually it binds to the enzyme somehow in a specific place called the active site. Often the active site has a very specific shape or structure that allows the substrate to bind to it. Sometimes that is so specific. It's called the lock and key method, where only a substrate molecule can bind in that spot. So my substrate binds to my enzyme. The enzyme holds in place. It brings the other reactant in just the right orientation to help them react. And again, it speeds the reaction up to a much faster speed than it would ever happen on its own. Okay? So that's real quickly how enzymes work. You'll learn a lot more about that when you take your biology classes. But that's the end of chapter 14. We're finally done. Hope that helps. Y'all have a good day.